Oh, so I try to stop. Anyway, so today we're going to discuss about the ammonia electric vehicle. So we discussed briefly last time. So we just go through really quickly about what we tried last week, and then we go through the rest of the PPT. So the key thing we are looking into an alternative fuel for the EV will be, we know the battery may not be a good solution. The battery do have a lot of issue regarding the energy management, the nighttime, recycling issue. So that's why we look for the hydrogen will be quite a good alternative, because in theory, hydrogen should be 100% renewable. There won't be any emission like the carbon dioxide. But however, hydrogen still have a lot of issues we're going to discuss in a moment, because hydrogen do have a problem of the high pressure, high costs, and time to the market. Many things still are a big issue. So that's why we're looking into other field. Yes. One, we do listen to and see, but this slide we cannot see. That's why just now I spent some time to go through using as another mechanism to double check that is the right recording. So that's why now I think I fixed this time. Sometimes they are not recording the proper PowerPoint. Sometimes only my face. Sometimes it's not my face. It's really confusing. So now then I use another one to do the recording to see. Hopefully that will be good. So today we're going to go for a number of areas, including why we think lithium battery is no good, and we are also looking into hydrogen. Will hydrogen a good solution? Would that be expensive? Or then we're looking into the ammonia-powered EV, and then we're looking into supply chain, ammonia supply chain as well. We're also looking into some disadvantages of ammonia power, and also a kind of the energy content calculation for ammonia, how much energy will be there. And then we're also looking into ammonia EV design, the whole EV design. So firstly, we're looking into the basic arrangement for different kind of the energy domain. So we know that classically we divide all the energy storage into electrochemical. which consider like all the lithium-ion batteries will be electrochemical and fuel cell, and also all type of battery like lead battery, lead acid are kind of the electrochemical. And another possible battery, the red dot flow battery, will require future technology for the energy storage. Electrostatic means we don't need to pass through any kind of the chemical reaction, just the electromagnetic or electrostatic method. We can store the energy like using the electromagnetic, like the superconductor and supercapacitor is also electrostatic method, and then we got inductor and capacitor. So those methods, we are mainly using EM mechanism to do that. So that's why the energy conversion rate will be really, really fast. We don't need to pass through any chemical. So that's why when we consider to use supercapacitor, the response time is so quick. So that's why for high current response, we can able to go for the supercapacitor, even though for the superconductor also be the same. But if you go for chemical reaction like this one, the response time can't be too fast anyway. Of course, mechanical one is more conventional. For the last 5,000 years, probably we all use mechanical energy storage. So that including the compressed air, pump storage, and also flywheel. And I think some time ago, we do see some flywheel vehicle, but that would be one of the good alternative. But however, flywheel vehicle still need to use a large momentum, large inertia to do the energy storage, may not be really convenient for a number of applications. And then we also have the classical chemical fuel, like including hydrogen, methane, and ammonia. Usually, we can either consider to burn them, like the ICE, to create energy. Of course, there's many other energy storage methods to do that. So if you look into the energy density, you can see that here is the map to show the energy density, which is also called the specific energy versus the power. You see, energy storage system, we require high density. We also require high power. So that means high power means we can able to create a lot of current and high W, high power watt. So supercapacitor, as I mentioned, like lithium capacitor, able to provide high current. So that means in some case, if we want to create really high energy power, then we can use that. But however, they're really expensive. Their energy content, so-called specific energy, like the WH per kilogram is not really good. But however, for other type of the energy storage, like fuel cell, because fuel cell mainly store the energy in terms of the chemical reaction. So like the hydrogen, you can able to store more energy. Like the ammonia can store more energy. Like the diesel also are kind of the chemical energy. They can usually store a lot of energy. And then the one in the middle is called the lithium-ion battery. Is somewhere these two in between. So I think in the future, if we go for energy storage, we should consider hybrid solution, a multiple combination. We should combine with probably fuel cell, lithium, battery, and also maybe lithium capacitor and supercapacitor. A combination able to provide us with a different requirement of the current power in different kind of the application or instance of the power load. One reason we can see that for the lithium and cobalt will be the price fluctuation. So I think in the last 5 years, I tried to look into the pricing for lithium. The price actually fluctuating quite a few times. Talk about in here, 14 units and that go up to 70, 5 times different in just a few years' time. So if any material, the price fluctuation that much, that would be end up with a lot of the problem for the manufacturing and production. Similarly, another major material for battery is the cobalt. Cobalt, you can see the price here are fluctuating so much as well. So that's also not a good method to use that material. The thing is, if I'm using the battery vehicle, highly depend on lithium and cobalt. At the moment, our range will be about 500 km. So that's a more or less 90% of vehicles on the market are only approach to 500 km. Maybe occasionally a few vehicles, a few brands can go for more than 500, maybe 600, maybe even 1,000, but only on a special design. So you can see that our limitation for the battery vehicle will be roughly about 500 km. If you want to go anything further, we do a limitation, or we do invest so much in the battery. And also, that's why we need to look into other energy storage, not only battery, but probably other type of fuel, maybe something like chemical fuel. we're also looking into long carbon base. So what kind of long carbon base fuel will be still available? There's so many fuels like the diesel, gasoline, but they are not long carbon fuel. So they're going to have emission. Even though when we use hybrid, then we still have emission. So lithium-ion battery, let's see what the issue of the lithium. Lithium battery will be, we are using them for a lot of the equipment like in here. Everything, we are now using anything related to energy storage, cell phone, entertainment, or wind power, solar power, we all use battery energy storage. So that will be make the lithium and cobalt price become really critical, because anything related to these two pricing, we highly relate to all the energy storage here. Some of them may be entertainment, may not highly depend on the battery, but for instance, for energy storage for the renewable energy, electric vehicle, electric vehicle, they highly depend on them. So that becomes a major issue for the battery if you only rely on battery. So if you look into the world production, for metal production, the first one goes to iron, second goes to aluminum. Then you can see that the other major material, those in the red color material are actually a major material for the battery. We're making battery mainly use lithium, cobalt. Sometimes we also use nickel and manganese. So that's why you can see that there's, especially for lithium, they're really rare earth material. And if you look into production in terms of mineral are not only metal, everything like the carbon A are also a kind of the mineral we are using. So actually the ranking go to 47. I point out the vanadium. Vanadium is another material we use heavily for the red dot flow battery. That will among the future battery we may go to use. However, there's still a problem of the supply because it's still slightly rarer. You can see the silver go to 21, gold go to 25. So that's why I can see that they're really close in terms of the world production. So if you look at the history of development of the trend from the early stage of the petrol car, and then go to hybrid, which last 30 years, and then today we are using lithium. But since we are not happy about lithium, we move on to fuel cell, like hydrogen fuel cell. Hydrogen fuel cell, we have problem. We've been trying to use hydrogen fuel cell for the last 200 years. Hydrogen fuel cell has been 200 years. And then we extensively tend to use hydrogen fuel cell vehicle for the last 20 years, but still not very successful. You can see the market, I think less than 5% are hydrogen vehicle. Why is that? Because there must be some problem. We later on try to examine what the problem is. That's why we propose another new vehicle for ammonia. That will have a lot of advantage. We're going to say more about ammonia vehicle in terms of why it has zero carbon. You see, for the whole world, there's only 3 gases on zero carbon emission that can be used for this kind of the energy storage. Of course, hydrogen is one of them. Another will be ammonia. Ammonia is NH3. There's a low C there. So that's to say, if you use ammonia as a gaseous fuel, we don't have any carbon emission. Even though we tend to use methane or other hydrocarbon fuel, there must be C there. Whenever we use them, we crack them, the C must become carbon dioxide, carbon monoxide. There will be emission, which we don't quite like. So that's why we try to examine more about the ammonia. So if you look at the vehicle, try to use the lithium as energy for the vehicle, we found that when we produce the battery, we have a lot of the carbon emission. Like this 100 kilowatt of the battery vehicle, then there's 7.5 tons of CO2 emission, which we don't quite like. And then if we try to use the EV to use a few more years, then we can able to compensate the emission. That compensation means we compare our EV to a gasoline car, how much CO2 we can reduce. If we do that, then it seems that we still need 2.7 years to compensate for the manufacturing of battery of 7.5 tons. So if all our energy comes from renewable, that means we use solar power or wind power to charge our EV, then we can able to reduce that to 2 years. But anyway, you can see that if we use any vehicle less than 2 years, we are not doing anything good for the environment. So if we, even though for smaller vehicle like the 40 kilowatt hour battery, we still need 1 year for compensation for all the CO2 emission. Anyway, the hydrogen is expensive. classically, we can divide them into green, blue, gray, and brown hydrogen. Only green hydrogen is acceptable because we are using electrolysis, so we can able to produce hydrogen at 100% zero emission. But another possible will be using pink hydrogen. Pink hydrogen is using nuclear. In a way, it's still quite zero emission, but still a lot of the issues related to nuclear we need to consider. Today, most of the hydrogen we get from the market, that means if you go to a gas station to charge with hydrogen, they mainly about gray hydrogen. Gray hydrogen means when we produce hydrogen, then we release all the CO2 in the atmosphere. So that's a nonsense. It's not a method we use for zero emission. Blue hydrogen, we try to capture it, but capture is always a problem. We capture it indefinitely for CO2. It's too expensive, impossible. So that's why they are all not good solution. So to do this one, another problem is hydrogen will be about the storage. You see, we usually, for classical information, we know that 1 kilogram hydrogen only have 33.6 kilowatt-hour. And then if the hydrogen is this amount of the density, then you can see that it's really much equivalent to about this consideration. The density of diesel is 0.85. 1 kilogram of hydrogen is roughly equivalent to 1 gallon of diesel. So some people, when they try to compare hydrogen energy storage to diesel, that's how they do compare them. 1 gallon of diesel roughly equal to 1 kilogram hydrogen. The thing is, hydrogen is really low density, really low, only 0.083 gram per liter. If we use this pressure or this kind of the density, we can't have any energy at all. So that's why we pressurize it to 700 bar or 350. That will be a 300 times higher density in order to make it possible to be used. But in this case, the storage tank like this one will be really expensive. Like this one, we need to use 100 kilogram of material steel in order to store 5 kilogram of 700 bar of hydrogen. So that's not really nice to hear that, because we are using too expensive, too heavy storage to store a little bit of hydrogen. And also there were high leakage. You store the hydrogen here 1 month, because really high pressure, you release by about 10%. So for long duration of storage, we cannot use hydrogen. So for the gas station, like in here, this picture, you can see that all the gas stations must be installed outskirts, because if you store them inside the city, it's too dangerous. Nobody will able to afford that kind of risk. And we cannot convert any gas station, like gas station in hydrogen. Today, we got another gas station. But after 10 years, if we don't need that many gas stations, we may like to convert them into hydrogen station, but that's not possible, because hydrogen talking about 700 bar, gasoline only 0 bar liquid. So that's why they are not convertible. Even though we're using LPG, 10 bar, they're still not yet compatible. So that means in the future, there will be a lot of issue for hydrogen. And at the moment, the price of the hydrogen is more than double of the diesel. If you want to fill up your vehicle, then you can see that you have to pay double. But that hydrogen only about brown hydrogen, not green hydrogen. I think if in the future we tend to use green hydrogen, will be 8 times at least. So that is infeasible. Nobody can afford that. So however, ammonia is the one I try to promote for today's lecture. Firstly, ammonia is NH3, only nitrogen and hydrogen, no C in the formulation. So that's why 100% it must be zero emission. And it's kind of new energy storage. Of course, in this case, we have more research content. If we propose a project for ammonia, we've got more research work, right? If we propose a project for hydrogen, million people will be working on hydrogen. But having said that, hydrogen energy storage may be too old-fashioned. But if we go for ammonia, then we do need some collaboration between electrical energy and also chemical engineering to do the work. So this concept, we try to work on this area. So if you look at the powertrain, then we have the ammonia here. We use cracking technology to crack the ammonia into hydrogen, and then we store directly, go to fuel cell. Actually, we don't like to store the hydrogen because it's too dangerous to store in a vehicle. Many of the government or fire department do not like us to store the hydrogen in the vehicle. So if low hydrogen storage of ammonia is much safer, low exposure. So that's why we have here ammonia crack into hydrogen and go into fuel cell directly, and then we use the fuel cell technology, MPPT, maximum power point tracking, to store them electrically in the battery, small portion of battery for temporary energy storage. And then you can go to motor drive. And then we need to measure, control all the flow control for each portion in order to have maximum power flow. So that means the key performance for this will be, firstly, ammonia have low carbon. So that means even though we use methane alcohol as a fuel, many people saying that, but you see methane and alcohol do have the carbon. If you use them, even though we crack them, we still have CO2, CO there. That is not a good future fuel. If you try to compare hydrogen need to store them at 700 bar or 350. These two are international standard. But ammonia only store 8 bar, so much safer. How much 8 bar? You see all the LPG gas, natural gas we use at home. At home, we are using gas, right? For the heating or the cooking, they all are using LPG, yeah. Or sometimes natural gas. They are pressure only 8 bar. So really much, that's the pressure we've been using for all the fuel. We feel comfortable, we are safe. So that means we are quite happy to use them. So ammonia, we can easily to compatible for all the gas station. Because all the gas station, like the natural gas station or LPG gas station, they always operate at 10 bar. So we just swap the fuel with ammonia. That will be completely convertible. And also, if you want to inject ammonia into a vehicle, like fuel in a vehicle, you only take a few minutes, 3 to 4 minutes. So therefore, it's much faster than battery charging. So let's see the energy content. So for a gas tank for 23 centimeter, about that, the diameter, and 1.4 height, the energy can store will be 22 kilogram ammonia. That equivalent to at least 56 kilowatt hour. So that will be more than 10 times compared to battery. So that's only at the moment I can do the research. In the future, I can also increase the number to much higher. So ammonia, that's why you can also come from many resources, not only synthesis, only using artificial synthesis. So in here, I have a demonstration. You got liquid kind of the ammonia, and then we have flow control, go to a cracker, we can crack them, and then each crack them into nitrogen and hydrogen. Hydrogen is a more or less inert gas, not really inert, but quite inert gas. It won't have any effect to the fuel cell. We can directly go to the fuel cell with hydrogen, we produce electricity. We do need a purifier to eliminate any remaining ammonia, maybe 0.01%, but we still need to filter them. So that's how I did the work in the lab. So that means we also need a gas purifier, as I mentioned, because there's even though 0.01% of ammonia in the channel, we still need to remove that. Because fuel cell, like the PEM membrane, are really scared about the ammonia, you damage ammonia. So we need to filter them. To filter them is quite simple. We have a lot of the chemical to filter them, like, yeah, so that is one of the chemical very similar to carbon. We can therefore absorb the ammonia. So after we absorb them, we can heat up, then the ammonia will go away. So very easily, that can be recyclable. And then we also have many other methods to absorb them. And for this, even the water, we can dissolve them very easily. All this gas, we can pass through a water bottle or a water filter. We're able to remove them. Or the liquid, we try to filter them. We can also using acid to neutralize the ammonia. So use sulfur acid. Reaction with ammonia become ammonium sulfate. We can very easy to react them. Even the hydrochloric acid become ammonium chloride. So we are very easy to neutralize them. Then we can also use some other membrane to filter them. We can allow the hydrogen to pass through, but not ammonia. Because ammonia H3 is a bigger molecule. So if we're using a very small nano membrane, we can pass through hydrogen and stop the ammonia. So that's the way we can able to do the filtering. Cryogenic, then we can use pressure and or using temperature, because ammonia it can become liquid. Yeah, I think minus 50 degrees C. So we can just pass through temperature controller to remove the ammonia. And hydrogen, the melting point of hydrogen will be minus 260 degrees C. So we can very easy to use temperature to remove the ammonia. So all these things are very well developed to the filtering. So here is two vehicles I did. So one is a golf car, which you can see that this first golf car I did about 4 to 5 years ago. It's the world first vehicle to use ammonia to power vehicle. And after 2 years, I finished off with the minibus. That's a 100 kilowatt of minibus. Also 100% to use ammonia to power them. So let's look at the supply chain. I think to make a vehicle become successful, we need to have good supply chain for the fuel. Let's look at the supply chain for different kind of the resources. For instance, for supply chain for hydrogen, then of course we need to use, sometimes we use natural gas to produce hydrogen. Then we use the reforming to crack the methane or other natural gas to form the hydrogen. We can also use electrolysis to electrolyte the water become hydrogen. That will so-called the green hydrogen. For the gasification, we can also convert other organic material. Most organic fuel, organic material have C, H, and O. We can therefore crack them to get the hydrogen. Of course, biomass, we can also, by using biomass degrading, we can also form the hydrogen. Sometimes hydrogen will also come with the methane as well. But hydrogen, we do need to store them. To store hydrogen, we need to store them 350 and 700 bar. So that's one of the issues we mentioned just now. Of course, we can store them in liquid hydrogen, but store in liquid hydrogen, I think the temperature requirement really, really low, minus 260 something degrees. That's really expensive to do that. But we can also look into solid storage. Solid storage, that means we are not solidify them, but however, we can store them in some kind of chemical, like metal hydride or some kind. So that means the hydrogen hydride. So a kind of the chemical we bond with the H. And another possibility is carbon nanotube. Today, because the carbon nanotube technology, we can store the hydrogen inside the carbon nanotube. So in this case, that's a much more convenient because they actually hydrogen molecule. So we use special technique to using the surface to store them. So when we want to retreat them, we just increase the temperature. We're able to retreat all the hydrogen. So that's a conventional way we can deal with the hydrogen. For transportation of hydrogen, then sometimes we use pipeline to do that, or we use truck or tank to store them. But most of the case, then all the hydrogen must be pressurized so that we can transport sufficient hydrogen, like at least 700 bar to do that. Shipping, sometimes we may use liquid hydrogen to do that. Of course, anything with liquid hydrogen, then we also require a lot of the support, like the temperature and pressure to do that. So that's why I can see that hydrogen has been talking about for 200 years. Last 20 years, we seriously to examine them. But because you can see that their technology is already here, but still we found that it's not being so popular. There must be some reason. Probably that reason could be due to the one I mentioned, high pressure operation, dangerous, difficult to go through the concept of the civilian, and everybody is scared about hydrogen. So that's why to teach about hydrogen, then we also need a refuel station. So where the location refuel station? You can see in California, we do have quite a few refuel stations, but they're all in the outskirts, very expensive to make one. So that's why nobody like to live near a hydrogen station. But however, you need hydrogen to refuel your car. So a kind of thing is contradicting. We like hydrogen station near to us, we don't like hydrogen near to us because it's too dangerous. So let's look at the supply chain for ammonia. Would that be better or equally difficult? For ammonia, then we can, of course, we can also using reforming to form them. What we need to do, reform using say natural gas, we can extract the natural gas ammonia there, or we can using natural gas, using reforming to crack them into hydrogen. Hydrogen we can combine with nitrogen to form ammonia. Combination of hydrogen and nitrogen to become ammonia is quite popular method. Electrolysis, you can also electrolyte the water, become hydrogen, and hydrogen we can combine with nitrogen to become the so-called green ammonia. So ammonia will also a different color, like green and blue, and similar naming for the hydrogen. Gasification, because the boiling point for carbon dioxide, carbon monoxide, hydrogen, and also ammonia are all different. So can very easily to use different temperature to separate ammonia from rest of gas. For instance, if a biomass generation or in the landfill, we usually have the methane and also the hydrogen and also the ammonia, because they all have quite different of the boiling point and also melting point. So that's why we are really easy to use temperature gasification to separate them. So let's look at quickly about how we do the extraction for this kind of the method. Now, firstly, we know that we can use nitrogen combined with hydrogen become ammonia. So nitrogen we can extract it from atmosphere. Then we can use cryogenic distillation to remove them. So that's one popular method. You can separate nitrogen from oxygen. So other than then we can use Haber-Bosch process. So that's a really popular process. We combine nitrogen with hydrogen, become ammonia. So that's what I mentioned just now. So this process is exothermic. That means you can able to provide 92 kilojoule per mole of energy. So that's quite nice to hear that. The temperature operation about 400 to 500 degrees C. So that's all already a really well-established method. We need to use catalysts like iron. Sometimes we iron mixed with potassium oxide and also aluminum oxide to accelerate the catalyst. The portion, of course, is 3:1 because N is 3, right? This reaction can able to go to equilibrium at about 200 bar and 450 degrees C. So if you have more temperature, then we can go to NH3. The other side will be lower pressure and lower temperature. So for this process, then because the cracking and synthesis, this energy balance have a divide by 2 because there's 2 in here. So to do this, then the theoretical energy to crack ammonia is 45.9 kilojoule per mole. So now there's a briefly about information of the Haber-Bosch process. So these two are roughly the same, only different by 2. The rest of them, the different due to other losses. This is only theoretical one. So let's see the storage for the liquid ammonia. So all the ammonia, we can liquefy them at about 8 bar at 20 degrees C. So they're really much convenient. Most of the LPG gas we use at home or other gas fuel we use at home in a container gas or propane, we are also using similar pressure. I think at home we use a lot of propane gas, and that's also similar to at about 8 to 10 bar. So the operation pressure are really much well established. All the containers are well established. So you can also liquefy them use 1 bar at minus 33 degrees C. So this pressure, this temperature is really much convenient. So this temperature is quite different from all the other gas about their melting point, about the boiling point. The boiling point for carbon dioxide is different from that, or for oxygen and hydrogen are all different from that. And so that's why we can very easy to use gasification to separate them. So another method to store the ammonia called this. So what we try to do, we'll use hydroxide, ammonium hydroxide to store them. Basically, we mix ammonia with water, become ammonium hydroxide. So this is just like so-called ammonia water. So we can easily store them at 20 degrees C, but the portion of mixture only about 25 to 30% ammonia can become ammonia water. So, but this method is safe. Of course, after we store them in the water, it won't evaporate so easily, so that become less volatile. Because sometimes pure ammonia, it may be irritating our eyes, so we need to resolve that. Solid ammonia, we can, for instance, ammonium chloride. Ammonia gas mixed with hydrochloric acid become ammonium chloride. Another compound would be we bond them together with metal ammonia that will also become a solid form. So this kind of solid form, we can quite easily to obtain the ammonia from this combination. Like heat up, we are able to release the ammonia. So that's another way we can easily to store the ammonia. So that means to store ammonia, we don't need to use storage tank. We can just using this chemical method to do that. But for hydrogen storage would be more complicated. For transportation, we can also using pipeline to store them, very similar to natural gas transportation. And then we can also use truck or tanker to transport the liquid ammonia. As we know, the liquid ammonia only need minus 33 degrees, so that's really easy to manage. So we can transport them in railway or road or shipping. That was international technology has been done. How to transport the ammonia. So, but we have been talking about ammonia, then I try to promote it. So, but of course, we also need to talk about the disadvantage. What's the con of the ammonia? So everything we got the pros and cons. So you can see that at the moment, the major problem for ammonia would be about the infrastructure. We don't have infrastructure for ammonia at the moment. We do have really good infrastructure for electricity, infrastructure for gasoline, or something we are now developing the infrastructure for hydrogen, but still developing. But for ammonia is completely new. So to catch up, to make the ammonia become the winner, we need to catch up with the infrastructure, how to build up the whole structure. The safety, ammonia actually is toxic, but the toxicity is much, much less than CO, carbon monoxide. So it's relatively safe. They're not that dangerous because we can smell them. When we smell the ammonia, like that's the smell in the toilet, then we can easily observe them, we can go away. So it doesn't mean hydrogen, we can't smell it, or CO, carbon monoxide, we cannot smell it, but anything happen could be really, really dangerous. So that means the safety, some people want to concern for ammonia, but however, because it's really smelly, we can very easy to manage about the safety. But if we try to manage hydrogen or other gas, we may not easy to manageable. The density, ammonia, good thing will be really high density, much higher than many other fuel. So that means we are able to use them as a replacement for the future battery. So that one good opportunity. And also compatible. So actually ammonia, if we don't use fuel cell, if we just burn them combustion, it can be feasible for the ICE as well. You can tune the ICE so that you're able to accept the ammonia, but we don't like that because that will produce NOx. So for the emission, in theory, if you use fuel cell to deal with ammonia, there won't be any emission. But occasionally, we only produce a little small bit of NOx, but that's only really small portion if you use fuel cell to do that. And for the production emission, the ammonia produced from the fossil fuel, like the gray ammonia, then you result in significant emission. So, but that may not be the case. The thing is, we don't need to produce ammonia using gray ammonia method. We can just get it from the landfill. In this case, that will free of charge. And the concept, many people still consider ammonia as toxic, so they little bit worry about to use ammonia as the fuel. So, but that will need some kind of education anyway. So let's look at the content about energy content between hydrogen and ammonia to see which one is better. So what do you think? Do you think which one can store more energy? Hydrogen and ammonia. Ammonia. In terms of correct. For in terms of gas law, we know that 1 mole of gas is fixed volume, but 1 mole of gas we got 3 hydrogen compared to hydrogen. So that means energy content for ammonia will be much higher, 50% higher. But of course, in terms of mass, is different. One gas molecule for hydrogen is equal to 2, but 1 gas molecule for ammonia, NH3 equal 14 plus 3 becomes 17. So ammonia in terms of the mass will be much lower energy density compared to hydrogen. But however, we tend to use volume to be our calculation because ammonia and hydrogen is so light. We won't compare them with the mass anyway. The mass all become really low. So we mainly compare with the volume. A fixed volume of vehicle, how much ammonia you can put on. So in here, you can see that according to gas law, all the gas has the same volume per mole anyway. So that's why ammonia should have a much higher energy density compared with hydrogen, 50% higher. So hydrogen is lightest gas. So that's why the energy content per unit mass must be much lower. And also there's when we collect ammonia, then there will be some energy management system needed to go in. There's some power loss anyway. So let's do a quick calculation to see how we understand about the energy content for ammonia. So in here, we can see that we try to decompose ammonia into nitrogen and hydrogen. So that's the formula. So 1 mole of this, you can produce half mole of nitrogen and 1.5 mole of hydrogen. So that means we got 50% more number of gas molecules. So the molar mass for ammonia is 17 grams per mole. So that means for 1 kilogram of ammonia, a simple division, you can get 58 moles of the ammonia anyway. So for 58 gas, because it's 2/3, so he all produced into hydrogen, crack them, then we can able to obtain 88 mole of hydrogen. So that's the energy come from. So this energy, so you can see that, but however, when we do the conversion to crack ammonia into hydrogen, we require 46 kilojoule per mole anyway. But this is only for crack them into hydrogen. So that means if we have 50% more hydrogen here, we can divide it by 3/2, then that means we only need about 30 kilojoule of mole per mole of hydrogen anyway. So that to say the net value for the energy will be, we got 241. That is what the basic energy will come from, minus the energy we need to crack them. So the left behind with 211 kilojoule per mole of hydrogen. So this energy content we can calculate back into how much kilowatt-hour. So eventually, we can able to get about, after all the calculation, we can per kilogram ammonia, we can get 5.1 kilowatt-hour. But of course, the efficiency for fuel cell is not 100%, only maximum 60%. So what we think will be for 1 kilogram of ammonia, we're able to obtain 3.1 kilowatt-hour. So that's the maximum. So that's how we can able to get the energy storage for the ammonia. So that brief calculation show us about what the energy look like. So you can go through to take out the exact calculation. So let's compare the energy content for hydrogen. So you can 1 kilogram hydrogen, then you got 500 mole. So in this, but the energy value for hydrogen will be 241 kilojoule per mole anyway. So 500 mole, we can do a calculation, we can get about 33 kilowatt hour. So if the fuel cell is 0.6, we got 20.1. So that's the energy for the hydrogen in terms of kilogram. So you can see that before ammonia 5, and now that would be 20. So obviously, in terms of kilogram, hydrogen have more energy storage. So let's do the comparison. Then at 60%, 1 mole hydrogen, we have this amount of the energy. To summarize, then 1 mole of ammonia will only 0.06, because that's in terms of volume. In terms of volume, ammonia have more energy. Yeah. So that means for 1 mole of gas at 20 degrees C, that's how the energy comes from. So you can see that in terms of volume, then we are able to produce more energy in terms of the nitrogen anyway. So that's roughly about 50% more anyway. So that's the table to summarize about the comparison. If you try to compare them with lead acid, you see the specific energy, that means energy density, kilowatt hour per unit kilogram, lead acid only 0.035. But just now we calculate hydrogen will be 20, ammonia will be 3.1. Lithium, if MC will be 0.2, but if only lithium iron phosphate will be 0.14. Then in terms of the volume, then you can see that ammonia have a higher energy density compared to them. Of course, that cannot be comparable to the solid fuel like lead acid and the lithium. So that gives us a summary how the 4 major energy compare to each other. So that's to say, in terms of volume, of course, solid type of battery will be much better. But in terms of the mass weight, then hydrogen is better, but ammonia is still good. And so that means if you want to build up an electric vehicle using chemical fuel, I think best way will be either hydrogen or ammonia. But for these two, in terms of the volume, then ammonia will be better. Okay, up to this point, any question? So this few lecture only show you about how we can calculate the energy content using some universal number to show you how the energy picture look like for ammonia and hydrogen, so that you can use the number quantitatively to go for a comparison. So we can see that the energy content in gas stage is not good enough. So that's why all the gas usually will be pressurized them. Like hydrogen, we pressurize them to 700 bar in order to store for more energy. So in theory, we pressurize 700 bar, we are able to store 700 times of the energy compared to 1 bar. But of course, in low pressure, then according to gas law, they linearly proportion, we can use the gas law, PV over T equal to constant, right? But however, when we high pressure, PV over T, that's gas law, no longer become linear, become non-linear. So we may not able to store that much of energy. But still, even though non-linear, the ratio is still good. I think not 100%, but maybe 80%. Anyway, let's look at that. For 700 bar, so that will equal 960 atmosphere pressure. That's really close to 700 bar anyway. For 1 liter, then we can, for instance, 20 degrees C, then the pressurized factor will be 1.15 for 700 bar. That is to say, we're not able to get 700 times because that's pressurized factor. Then we use gas constant. Out in here, there's a gas law. Then after the calculation, then we know the number of mole will therefore become 24, I think, rather than the other one. So if you use pure gas law, then we got some other number, but using this kind of the pressurized thing, we had 24.9. So at 700 bar, then we can therefore calculate about the energy content per liter will be 1.6 kilowatt hour. So for 1 liter, 700 bar, we're able to have 1.6 kilowatt hour of energy. So I assume then if we due to 60% efficiency, we got only 1 kilowatt per liter. So that means if you use hydrogen, roughly get 1 kWh per liter at 700 bar. So that's quite a good number we can memorize. So let's do the similar calculation for ammonia. Then for ammonia, then we are not going to store 700 bar. We only store 8.55 bar. But under that one, that already become liquid. So we don't use gas law to do that. Then for liquid ammonia per liter, we got 0.6 kilogram. Energy density for ammonia then will be 5 point something kilowatt per kilogram. Then after that calculation, we know that the energy content per liter of ammonia will be 3.18 kilowatt hour per liter. At 60% efficiency, we have 1.9 kilowatt hour. So this is 1.9. So you can see that compared to previously about 1. So that's to say we can have some advantage. So, but the thing is that is endothermic. So when we crack the ammonia, the hydrogen, we need to input energy. How much energy will be needed? So usually require 45 kilojoule per mole of the cracking energy to crack them. So that means 45.9 kilojoule per mole. We need to change them into kilowatt hour by 3600. And then we know that we have to use the 0.1017 kilogram per mole of energy to convert them. So the end up will be about 0.75 kilowatt hour per kilowatt. So this is the energy we needed to crack the ammonia into hydrogen. Yes?
Why we 60% efficiency of
Using 60%? Oh, 60% is the maximum for all the fuel cell. We cannot have fuel cell efficiency more than 60 from all the research paper. But probably for more practical, if you don't have good fuel cell, you may use 50 or 55, maybe 45. But 60 is the maximum we can get. So in this calculation, we try to do more favorites to work fuel cell technology. I just show you an example. You can play around with the number to use your own experimental number. Not 60%, you can use maybe 51% or whatever. So that means so we now can get it. When we want to crack the ammonia into hydrogen, then we require every kilogram we want 0.75. 0.75 is the one I calculate here. But of course, in practice, we may need to use slightly more because of power losses. So anyway, after I could do that, then we can look into the density of ammonia 0.6. So to multiply them, then we can get 0.46 kilowatt hour per liter. So that is the requirement. So now then, this original energy, so minus the cracking requirement, we got 1.45 kilowatt hour. So 1.45 in here compared to this one. So now we do a summary. Just now, the summary before are using kilogram, but now then, we look into analysis using kilowatt hour per liter. So hydrogen, we can get about 1 kilowatt hour per liter. That will be at 700 bar. But for ammonia, if we liquefy the ammonia, that will quite straightforward to liquefy them. We got 1.45 kilowatt hour per liter. So we got nearly 50% more. We don't have 50% more because this 0.05 go to cracking. We need to crack them. Okay. So that's why from this table, you can see that in terms of volume, ammonia have more energy compared to hydrogen. Yes?
I have a question. Can you go back 2 slides to the hydrogen slide? How do we store hydrogen at 700 bars? Like we need energy to store it in 700 bars, right?
That's a really good question. The thing is in here, just purely to say if you got 700 bar of hydrogen, how much energy you can get, that will 1 kilowatt hour per liter, without consideration of your thinking about energy storage requirement for the hydrogen. To store 700 bar is really expensive. Firstly, not only the storage tank, but you need to really pressurize them to use high power to occasionally to pressurize the container. So that you require a lot of energy. I haven't done that energy yet. But that's why
If we also consider that it would be like what, down 50% more?
maybe I give you a figure. If you completely seal on 700 pounds, because you can, in theory, you can seal them like in here, like this tank. Like this one. We use pressurize them, 700 pounds, inject in here, and then shut off here. But even though how good we shut the system, we still have 10% leakage per month if you don't do anything. So if we need to release in the atmosphere, then we don't need to use energy. We don't need electricity to pressurize that. But if we want to make sure that that can seal properly, we need to use electrical power to confine the location here. That will be energy losses. So you can see that we have 10% of the energy loss per month. So that means if you use them within a few hours, there shouldn't be any problem. If you store the long duration storage for hydrogen, that is not the solution. You need to use ammonia. So now then you do a comparison. So per liter, then we are much better off in here. Yeah. If we want to liquefy them, then of course, then liquefied ammonia will have much better energy storage compared to 700 bar of hydrogen. Anyway, so number 9 is the ammonia vehicle design, how we design vehicle using ammonia. So you can see that we firstly have liquid ammonia here. We pass through a flow control regulator to regulate how much power flow to the whole system. So if we require high power, then we need to increase the flow in here. That flow control system it's just like a valve. And then we can control it with a cracker to decompose in the nitrogen, hydrogen, and a little bit of ammonia. And then this ammonia usually about 0.1%. Then we crack them, then become purely nitrogen and hydrogen. So in here, then we can store them in a temporary store tank. This can store them at 1 bar or 2 bar. That would be much safer. And then this nitrogen, we can then go to the fuel cell. And there are 2 methods we can do in here. One will be use absorption method to only separate the nitrogen and hydrogen, only convert the hydrogen to the fuel cell. But that will be another expenses. So what I did, we just put the nitrogen and hydrogen both together into PEM membrane. Because PEM have no reaction with nitrogen. Nitrogen is really much more inert gas related to PEM membrane. So you won't have any damage to the membrane. So we just all 2 together go to our fuel cell. And then it becomes electrical power. For vehicle design, that's how we design them. So the battery storage still needed because we need electrical battery power for power regeneration. Fuel cell itself can only output power, cannot do power regeneration. So the motor in here, when we obtain the power from here, store in the battery, and then control the power through the motor controller to adjust the motor speed and motor torque. And then for the DC voltage link here, then we need to a supercapacitor, which are able to provide high power. This high power will be important, especially as I mentioned before, when the vehicle in the start up or overtaking or going down the hill, then we need high current for power generation. Then our ammonia fuel cell will be here. In power up, all this will be coming here. The ammonia fuel cell will provide us. Then we need to power conditioning. Because the voltage come out from the fuel cell may not be too stable. Usually that will power electronic power conditioning system to stabilize the voltage and current and go to the DC link. So this DC link will therefore become our middleman in order to connect supercapacitor, motor, ammonia, and battery all together. So the output of the fuel cell are actually stored in the battery. That's a quite good buffer. If you don't store them, then we need to always turn on the fuel cell. Sometimes we only turn on the fuel cell when there was some location more suitable. For instance, we can turn on the fuel cell at night when nobody using the car, then we can have a much better location to do that. We always turn the fuel cell in a more optimized mode. We try to tune the fuel cell into optimized operation. In certain kind of operating point will be better for fuel cell that will relate to temperature, flow rate, and output power. So we need these three parameters to control the best operation for fuel cell. So, but however, this best operation doesn't mean it's the requirement of output power. So that's why we need the battery to compensate for any power, high power and low power that required by the motor. For instance, if the motor suddenly require high current, fuel cell not able to cover them, then will cover by the battery. If you're not able to cover them, the supercapacitor able to cover it. So that's how we control the whole power management configuration. So that means that BMS relate to ammonia, supercapacitor, and battery, how we connect them up. So that require a dedicated design for the battery management system, or so-called energy management system. As you can see here, our supercapacitor will therefore connect in parallel. Although we say in parallel, actually they may not connect in parallel. Between them, they have a converter to connect them, because we are not able to get exact voltage between battery and supercapacitor. So usually there's different voltage. So between them, we have converter to convert this voltage to the battery voltage. And also, sometimes the supercapacitor really expensive. We may not able to have a full number of cells for the supercapacitor. Supercapacitor 2.7 volt, and the battery 3.7. So that means even though we connect up these two voltages are different, so we need a converter to catch up with these two voltage. So the motor usually directly connect to the DC link, which is the battery, through a motor controller, which is an inverter. So a power connection system is need to convert the battery voltage to low voltage to other control electronic. Because in here we need another control electronic to control the ammonia fuel cell, the cracker, or the isolator. So all the electronic, although they're low power, but all the power will come from the battery, because the battery will be more look like central energy storage. You can provide quite a good number. Usually that will be 10% of the ammonia fuel, the ammonia energy content. That should be good enough. Next thing to examine about the supply chain for ammonia. So we've been talking about ammonia for quite some time, but is it possible we're able to develop the supply chain? Without the supply chain, then it's impossible we can able to develop the ammonia vehicle. So firstly, we know that ammonia has been heavily used in agriculture and in some energy storage. Then we know that Haber-Bosch process, we're able to combine nitrogen and hydrogen. You see, in about 50 years ago, 100 years ago, we don't have sufficient fertilizer for farming. So, and then Haber-Bosch developed this process. They can artificially to combine nitrogen and hydrogen, become fertilizer. So since then, we have this fertilizer become in existence rather than naturally to come out from the biodegrading. So that means this kind of Haber process has been used to synthesis the ammonia from nitrogen and hydrogen. Just now I showed you how the synthesis, that's exothermic. We can therefore get it quite easily. Then since then, we can able to use ammonia for the fertilizer. So this process now can be reviewed for energy storage. Since ammonia is quite a good energy storage, so the Haber process not only produce ammonia for fertilizing, but also can produce ammonia for energy storage. So we need to build up the supply chain, how to produce the ammonia from Haber process or from other means in order to go to the next stage of the supply chain. Then for the whole world, we can see there's a lot of the good supply for ammonia, naturally, from the fertilizer plant or the landfill. So here, for example, in South China, there's a major company. We're able to produce really massive number of tons of ammonia since this year. And then in Malaysia, Brunei, Singapore, Indonesia, we all also have really good supply, much bigger than South China produce ammonia. So that is to say, wherever produce ammonia, we can not only for fertilizer, but also for energy storage. So that is to say, we don't need to worry too much about the supply chain. We already have a really good supply chain, but however, this supply chain only for fertilizer. So we talk to them and say, can you give a portion to us for our electric vehicle? So figure out how to convert, how to translate this kind of the ammonia into our electric vehicle. Probably that will be due to using some shipping or pipeline to deliver the ammonia. At the moment, we don't have that, but can assure to you, we do have very good resources for ammonia. So the transportation, we can, of course, there's a well developed, we can use pipeline to transport them because ammonia is much safer, only about 8 bar. So the transportation using pipeline will be much more convenient. And then road transportation, we are using pressurized tanker to do that. And then truck we can use in highway movement. Railway also we can able to do that. So I think we do have a railway system directly from Singapore to China or Singapore to Europe. So that means you can use that connection to deliver the ammonia from Malaysia to the rest of the world. For safety, I think many people talk about the safety will be something we have big concern. How can you assure that ammonia will be safe? So you see, ammonia is slightly toxic, and it can be also become hazardous. So that's why we need to stick really nicely with all the other restrictions for some safety restriction. So we need to train all the transport engineer to understand how to handle the emergencies. Some facility will be needed in case of leakage, and also some urgency response strategy. But how we know that one thing with ammonia sensor will be much lower cost than hydrogen. Hydrogen sensor really expensive. So that means the hydrogen vehicle or hydrogen plant, they cannot install too many hydrogen sensors because too expensive. The price for hydrogen sensor compared to ammonia at least 10 times. So that means if a vehicle we maybe only install 1 to 2 hydrogen sensors. In the manufacturing plant, we can't install many. But ammonia is different. The sensors really low cost. And so that means in case of only leakage, we can use water dilution. We can dilute all the ammonia because ammonia is dissolvable in the water, but hydrogen is not. So we can't use water to eliminate the problem of hydrogen, but we can do it with ammonia. Then water can also reduce its concentration. Then, of course, the ammonia water, we may say, oh, it may contaminate the environment, but ammonia is a fertilizer anyway. Even though we pour them into the land, it becomes a fertilizer. So that may not be too much a problem. And chemical neutralization, we can use hydrochloric acid to neutralize them. So that means ammonium plus hydrochloric acid become ammonium chloride. So that's a really common kind of the chemical salt we use for fertilizer. Then we also need some protection gear because ammonia actually is slightly toxic and also hazardous. So we need to use protection gear and some respirator in order to eliminate us from direct contact with ammonia. Goggles will be needed so that we are able to protect us from our eyes. Ventilation will be needed. But having said that, ammonia is only slightly toxic. I think probably 100 times, maybe 10 times less intensive than the carbon monoxide. So that's why it's really safe anyway. For distribution of ammonia, then we also looking into various ways to distribution. Certainly, we need a central location for ammonia for storage and then distribute to the land user. Then we can use pipeline bulk transportation, and then we can transport them using a small facility and also some fuel station. For some fuel station, we are thinking about to retrofit to convert all the LPG gas station into ammonia. As I mentioned just now, they operate at similar pressure. Similar pressure, that means we don't need to change the tank, we don't need to change the control, we don't need to change all the valve. We can use the same method to do that. So that means existing gas station, we can very easy to retrofit them. And then next interesting to see will be there will be any major player in ammonia. Would that be only me or my team to look into that? So at the moment, there's a number of the major manufacturers are working on ammonia. For example, like CF Industry and Jefffer Industry, they're also working on ammonia. So they actually have a production, like this company have produced 1.4 million tons of low carbon ammonia plant. So they actually, a lot of work has been doing in United States. And Jefffer actually have just activated a 48 ownership in agreement to produce 500,000 metric ton low carbon emission. Yeah. So this will be going to produce to Japan for their farming. So here is the link. You can see more detail about what they're doing. Jefffer International is also a big company in Norway. So they also are producing hydrogen. But they also now also working in ammonia as well. They have two hydrogen and ammonia. So they are working in so-called the renewable hydrogen ammonia using the new energy like the wind power and solar power to produce the clean ammonia and hydrogen. Nutrien is another United company. So they also have a really big production of low carbon atmosphere and ammonia. So the production up to 1 million tons. So that's also quite good and producer. The ammonia are so-called the zero carbon. Zero carbon, that means they have to use either electrolysis or using blue ammonia method to do that. So they capture the production for CO2 emission. So their annual production 180 million tons. So about 80% are used for fertilizer. The rest of them are for use of other production. So you can see that now we are in a competition between the ammonia fuel and fertilizer. So that means if we, in the future, we try to promote more ammonia power for electric vehicle. So that means we do need to increase the production for ammonia, because ammonia have been now being used extensively in fertilizer. But you can see that the world production is still really good. So that is to say, to increase the production could be much easier than increase the production for hydrogen. For hydrogen, production is still expensive. The transportation is also a problem. The storage is a problem. Ammonia, once you produce them, the storage will be much easier. When you store ammonia in a tank, after 1 year, there won't be any leakage because they operate at very low pressure. But hydrogen is different. Once you produce them, you need to use them straight away. After 1 month, 10% will disappear. You can see that if you ship the ammonia, ship the hydrogen from the United States to Japan, for example, it may take you 1 month to do that. By the time you get there, then 10% of hydrogen disappear. By the time you use them, maybe 20% disappear. And then that's why we don't think hydrogen would be a good way for the global energy economy. So that means ammonia should be one of the solutions to do that. Any question up to this point? Here, this lecture just go through the key point for ammonia and give you some number to show you how the basic energy calculation, how the ammonia data look like as compared to hydrogen. So here will be a green ammonia production, how we're going to go through the whole process. You can see that the energy requirement to convert into ammonia, we can use green power, like wind power and ammonia. So that can be used then to generate hydrogen first. So hydrogen will come from water. We can do the electrolysis, electrolyte the water into hydrogen, and then combine it with nitrogen to produce green ammonia. So green ammonia is what we want. Then once we get green ammonia, then that can be go to agriculture, and then can go to the hydrogen storage, and I can also go to other industry. So that's the picture from nutrient, this industry. I think in the future we will have another branch here to become electric vehicle. So that's how we're hoping. At the moment, the world production for ammonia is so huge. Just like United States, one company can produce 180 million tons. So just now we can see that how much 1 kilogram of ammonia, 5 kilogram ammonia got 22 kilowatt hours. So that means we can able to use a portion of ammonia to power the vehicle. But of course, in the future, if all the vehicle become ammonia, we need to increase the production here. The good thing is ammonia can be make use of green production. You can only use hydrogen and nitrogen to combine them, become ammonia. So that's why we do have a lot of the good future by using ammonia. Another major player is called Fertilizer in Canada. So they are also one of the major company. They are production, they now invest 30 million to increase ammonia production. So that means it seems ammonia have been working with across the industry they tend to increase their supply anyway. So I think they do know that there will be good opportunity for ammonia. Another company, Adrian, in Canada, they also are very good player. They're mainly about the distribution, they're not production. They also do a little bit of the production, but the main job will be distribution. This company are mainly doing the production. After they produce, then you go to this company for the distribution. These two companies, although they deal with some production, but the main job is to distribute the ammonia. And then for Cargill, they're also working on the trading, and also Lucia Defense, they're also working with international trading for ammonia with the rest of the countries. Like this company, they are also making a floating renewable energy solution. So just like what I mentioned about floating solar wind, so the storage renewable energy solution, they're thinking about using floating method. So that means using, say, floating solar, they are able to produce hydrogen as well. So next, after we've seen all these possible producers over the world, so you can see that the market is well known now. So there's not a really good connection, really good supply chain for production, distribution, and trading. But we just don't have any connection to build our own EV plant related to ammonia. So we need to somehow talk to them so that they are able to deliver the ammonia back to our charging station. So to design an EV, that's quite simple. We can look at some figures, how we're able to design an ammonia truck. For instance, if our truck is 100 kilowatt of the power rating for the motor, the truck will be 2.5 tons. We decide to have one charge about 500 km. So that means the energy consumption for the truck will be roughly 3 kilometers per kilowatt hour. So let's look into about how we design the vehicle. Assume that the ammonia energy content will be 1.45 from previous calculation. So 1 liter, we have 1.45 kilowatt hour. The density for ammonia will be 0.6 kilogram per liter. So how are we going to do that calculation? Have a quick think about it for a few minutes. Very simple and straightforward. Don't look at the answer yet. So this sample to illustrate to you how we can design an electric vehicle using ammonia rather than battery. So based on this basic parameter for vehicle, how we're going to calculate a requirement for the ammonia system. Yeah, huh?
You want us to?
Yeah, try that before I go through the answer. Yeah, try that. I think you only take you 1 minute to finish, maybe half a minute, maybe 15 seconds. Very simple.
Multiply by 0.333.
Yeah, then
Divided by
you,
1.4.
yeah, very simple. Yeah, just now you did that. So just like that. We are, the vehicle need to travel 500 km, and then we divide it by the energy density. So the requirement energy will be 166 kilowatt hour. That is the energy required by the vehicle. And then for the ammonia density, we know that 1.45 kilowatt hour per liter. So that means 115 liter. So again, the density will be 0.6. Then the total mass for the ammonia will be 70 kilogram. So that's really good. You can see that if you design an ammonia vehicle for 500 km, the ammonia requirement only about 70 kilogram. So you can compare to a truck. Usually a truck will be 10 times, or maybe half of them will be battery. But then using ammonia, we got the potential only using 70 kilogram for travel 500 km. That is wonderful, right? If you want to go for 1,000 km, we can put 210. That is only one minute.
140.
Yeah, about one person. But we can also swap the 10. You can see that in the highway, they've got a lot of charging stations. Go to one station, wait for 2 minutes. You can swap the 10, then you can just go. The 10 is only 70 kilograms, really easy to handle. So that's why you can see that why we need to promote ammonia, because that's simple, easy, low cost, everything look good. Not dangerous, ammonia can be shielded. Even though there's leakage, we can smell it, but of course there won't be any leakage anyway. So from this number, you can see that the future potential for ammonia vehicle is really highly possible than battery. Battery have a lifetime problem, can use for 7 years. But ammonia don't have any problem because it's nitrogen, hydrogen, don't have any recycling or any aging problem. Now, of course, you may think there will be aging problem for the fuel cell. Yes, fuel cell is only consumable. Then that means the lifetime for fuel cell will be equal to the lifetime for the system. That will be some time you need to change maybe the fuel cell. Occasionally, you need to renew the PEM membrane. That's the only material cannot last for 5,000 cycles. I think today the PEM membrane, they can use for about 1,500 cycles. But if you use them properly, you can use them 5 years, 6 years. But if you don't use them properly, you need to change them for every few years. But still reasonable. So the whole vehicle highly reliable anyway. Then let's see if how that look like. So we still need about small battery to come with the system because not only purely fuel cell. So because our batteries for temporary energy storage, fuel cell can only output energy, cannot accept. So the vehicle still need to brake, going down the hill, power generation. So we recommend to add about 20 to 30 kilowatt hour of battery to assist the whole phase. So the estimate for that vehicle design, how we estimate the power distribution look like. The body will be 1.5 tons. The motor 300 kilogram, the fuel and cracker will be 300 kg, the nitrogen tank will be about, the tank will be about like 100. Tank system, the battery 100, so total become 2.5 tons. So that's how the distribution for the whole things. So that means the whole thing here does not require too much about excessive material, excessive component. So to conclude this chapter, you can see that we really possible we are trying using ammonia to replace the battery. So that's something we like to see that. And we know that lithium and cobalt may have the end of lifetime. The thing is, firstly, the lifetime for battery only about 7 years, maybe 1,500 cycle. The price are really fluctuating. We think based on lithium and cobalt for battery do have a major problem, not only for manufacturing, but also for recycling. Although hydrogen is good, but we did not see its rapid development for the last 20 years. So, but however, ammonia could be a really good alternative fuel to hydrogen. Then we need to resolve the problem for hydrogen, including the safety, the cost, supply chain, and high pressure. So all these things happen in hydrogen, also happen in ammonia. So we know that ammonia may not able to rely in short period of time. I don't think ammonia become popular in next 2 years, 5 years. It may take 10 years or so to become popular, but we know it's a good thing. We start to do the promotion. So, another thing we know the advantage for ammonia will be it's really easy to detect and much lower risk for explosion compared to hydrogen. And the pressure much lower. So that's how all these things make the ammonia become more realistic. The energy storage for ammonia much higher than lithium ion, at least 10 times, and also 50% better than hydrogen in terms of volume. So for operation for lithium battery vehicle, usually mass is major issue. 50% of the mass of the battery or the vehicle will go to the battery. And then in this case, for ammonia and hydrogen, they both really light. So in terms of energy density, in terms of kilogram may not be too important for ammonia. The most important will be the volume. So in a gas tank, we can able to carry 500 km. That would be nice to see that. Ammonia has been a really good supply chain in the fertilizer. So we just need to have some modification for supply chain for ammonia so that we can make use of them to power up our vehicle. So what's the next step we have to do? I think we all talk about me to talk about ammonia for quite some time. So what you think about next step is to ask you to do the promotion for ammonia vehicle. I think first thing we can see there we need to do will be need to develop the supply chain. Without supply chain, we are impossible, we are able to rely the ammonia vehicle. So that including how we're able to support the ammonia production, distribution, and utilization, and also the trading. We need a very robust supply chain to do that. At the moment, the supply chain are well developed for fertilizer, but not yet. So all the supply go to a farm, not to the city. We need to convert them, give us a portion to the city to build up our supply chain in the city. So that's the thing we need to do. And also expand the vehicle type. At the moment, my research we're only working on a golf cart plus a truck. I think in the future, if you want to attract more users, we think about for go to the private car and also other commercial vehicle, because they both require long duration of requirement. For example, like a truck, they are good delivery. They usually require the vehicle to travel for 1,000 kilometers. So that means we need to build up some kind of the charging station, maybe heavy 500 km. That will be easy enough anyway. We also need to standardize all the technology. At the moment, we don't have any standardization for the gas tank. I'm just using a standard tank 1.4 meter. So in the future, if we can standardize them, that would be much easier for global use as well. At the moment, I use really thick tank. They are very expensive. But you know, LPG thickness of tank also could be good enough. We are using LPG gas for cooking. And so in this case, you can see that the tank is really light, very thin. We can use same kind of gas tank to store the ammonia, but we need to find a way to standardize them. And then next thing is to public awareness. At the moment, nobody understands ammonia, only very few, only my students. Right? So we need to do some promotion to tell them what's the advantage for ammonia and vehicle, why we need to use them, why they're good fuel compared to hydrocarbon fuel, compared to hydrogen fuel. So every time they make sure everybody understand what it is. Without understanding information, they can't make any decision. And also the conversion optimization. So we will look into the whole process. Would there be any way we can enhance the conversion optimization? You know, the Haber process is exothermic, but when we want to crack the ammonia is endothermic, we will inject energy. So how are we going to inject the energy properly? Where the energy comes from? It comes from battery. How to can minimize the energy, and how to make sure the whole system more reliable, every part was more effective. So that's the thing we need to optimize the whole structure. And then, of course, in the future system, we need to use them to replace all the coal-fired power stations. At the moment, power generation are mainly nuclear, coal-fired, and renewable and natural gas. So I think in the future, if we replace all the coal-fired and natural gas by ammonia, that would be a nice thing to have. Coal-fired have a lot of the emission. Major emission come from here. Even though we use natural gas, we still have CO and CO2 emission, which I don't like that. But if we're able to use ammonia for power generation, then we have zero emission. So why don't we think about to use ammonia to replace natural gas? I think natural gas is only interim solution, not the major solution, because it still produces carbon dioxide. So that's some references you can see. And if you'd like to explore more about my development here for the ammonia vehicle, so I think there's one paper I present in Hong Kong. The other paper I from IEEE. You can get that, and there's a YouTube. You can see what I present in the YouTube. So finally, I think zero emission energy is our major goal. So that means carbon neutral synthetic fuel, so for in strength for hydrogen and ammonia. So that means even though we are using a lot of carbon neutral synthetic fuel, like we try to combine CO2 with some other material, becomes hydrocarbon. But that kind of fuel, although people saying that they are zero carbon because they absorb the carbon dioxide from the atmosphere to create a synthetic fuel. But when they burn the fuel, they still produce CO2. Although they say, I'm just using the CO2 from the atmosphere, so I'm not actually producing any CO2. But still, by using this method, you still have a genuine CO2. I like to eliminate all the CO2 from the atmosphere. I want to reduce the CO2, go back to industrial sense. To do that, we need to continuously to remove the CO2 from the atmosphere. Only thing we do will be using hydrogen or ammonia. Of course, my code here will be don't use synthetic, they're still no good. I like to use 100% zero emission fuel without any doubt. So that's my contribution. Any questions? Good. So near the end of the hour now. So probably now we can end here. So this chapter mainly to go through my previous project for ammonia. Then you can know briefly about how we deal with the ammonia, how we're going to work with the hydrogen. We're not trying to eliminate hydrogen. I think hydrogen is still good. We're not facing the future position for hydrogen yet. But I think ammonia will be a good source to support the hydrogen, will be a replacement. Hydrogen have been developed for the last 20 years, really good, nicely, really good hydrogen economy, but we are not trying to destroy our hydrogen economy, but we try to work in parallel with hydrogen economy. But when you work in parallel, the next step will be to see which one is better, how much portion for each one. That's good. Okay, thank you. Then see you on Thursday.